Okay, let us start. Just confirm whether you can hear me and also see my slides. Okay, so welcome to week 4 live session. Today we will be solving the fourth assignment. Okay. So given that kinetic energy of alpha particle in an alpha decay is 7.68 MeV and Q value of that alpha decay is 7.82 MeV, what is the mass number of the parent nucleus? Okay, so as we know, so this question will require concept of previous week. Actually, we also had a problem related to this Q value and alpha particle kinetic energy. So let me say it briefly again. So if it is alpha decay, then suppose the parent nucleus is X and the daughter nucleus is Y. So the atomic number of the daughter nucleus will be Z-2 and atomic mass will be A-4, and then one alpha particle will come out, which is the helium nucleus. Okay, and so the energy conservation says mass of that parent nucleus times c square, which is the energy, rest energy, is equal to my c square plus m alpha c square plus kinetic energy of alpha particle plus kinetic energy of the daughter nucleus. And Q value of the reaction is basically mass of X minus mass of Y minus m alpha c square, and that is equal to kinetic energy of alpha plus kinetic energy of Y. Okay, and from momentum conservation, we know that momentum of X is equal to momentum of the alpha and daughter nucleus, and in the rest frame of X, Px is equal to 0, so Py plus P alpha equal to 0, or momentum of Y is minus of momentum of alpha. Okay, and so the magnitude of Py is same as magnitude of alpha particle momentum, and since the rest energy of alpha particle is much higher compared to the typical kinetic energy, so as you can see, kinetic energy of alpha particle is few MeV, whereas the rest energy of alpha particle is 4 atomic mass unit, or which is nearly equal to 4000 MeV. Since it is much higher compared to typical kinetic energy, we consider non-relativistic expressions to write down the kinetic energy. Okay, so the kinetic energy of alpha particle will be P alpha squared divided by twice m alpha, and since Py is magnitude of Py is same as magnitude of P alpha, so you can replace Py magnitude with P alpha magnitude and then write it down as so that kinetic energy of Y can be written in terms of kinetic energy of alpha particle. And once we know that kinetic energy of Q value of this alpha decay, as we saw, Ty plus T alpha plus Ty, and so T alpha into 1 plus M alpha divided by My. So this is the expression that we need to use here. We have to find out what is the mass number of the parent nucleus, right? So, and so from here, Q alpha over T alpha 1 plus M alpha divided by My. Let's say A prime is equal to A minus 4. So this can be approximated. So M alpha is 4 atomic mass unit, and My, that is mass of the daughter nucleus, is A prime atomic mass unit. So 4 divided by A prime. From here, Q alpha by T alpha minus 1 is equal to 4 by A prime, or A prime will be equal to 4 T alpha divided by Q alpha minus T alpha. So that is equal to T alpha is 7.68 MeV and Q alpha is 7.82 MeV minus 7.68. If you evaluate it, you will obtain, let me check, you will obtain 219.43. So this is A prime. We need to answer the mass number of the parent nucleus. So that is A. So A prime is A minus 4. So this is equal to A minus 4 This implies A is equal to 4 plus this quantity, so 223.43. Okay, fine. Okay, in the beta decay of Sn to Sb, the maximum kinetic energy of the electrons emitted is found to be 3.2 MeV if the atomic mass of Sn is this and the atomic mass of Sb is what we have to find out. So, okay, so as we know, in beta decay, so this is basically beta minus decay. So a neutron is getting converted to a proton, atomic number remains the same, plus electron comes out plus antineutrino comes out. Beta minus decay. Okay. The maximum kinetic energy of the electron emitted is found to be 3.2 MeV. Atomic mass of Sn is equal to atomic mass unit. What is the atomic mass of question mark? So let us, okay, so basically for this reaction, Q value of beta decay we know is maximum kinetic energy of the electron. Okay, and what would be the Q value of this beta decay? That would be mass of X minus, but these are all nuclear mass of Y minus mass of electron in atomic mass unit, let's say. In order to convert all of these to the atomic mass, let us denote the atomic mass by M. So since these atom will have Z number of electrons, so in order to convert it to atomic mass, we need to subtract Z number of electrons mass. Likewise, we convert it to atomic mass as My minus, but the atom Y will have Z plus 1 number of electrons in it, so that's why we need to subtract Z plus 1 number of electrons mass, right? So Q value of beta minus decay becomes, this get cancel out with this Z, and this one will again cancel out with this. Okay, let me not do this here. So this is basically atomic mass of X minus atomic mass of Y. Okay, so in our problem, X is nothing but Sn. So here the beta decay is Sn 5127 becomes Sb 51127 plus electron plus antineutrino, and Q value is, so that is nothing but 3.2 MeV. So therefore Q 3.2 MeV is equal to mass of Sn minus mass of Sb, but these are atomic masses. So, and we need to figure out what is the mass of Sb in atomic mass unit. So mass of Sb will be mass of Sn minus 3.2, but we need to use this relation between atomic mass unit and MeV. 931.5 MeV, right? Yeah. Mass of Sn is this quantity. If you evaluate it, you will get 126.906925 atomic mass unit. Okay, so the correct option is A. Let me know if you have any doubts. where are we using relativistic case? This problem, we said we are using non-relativistic formulas because the mass energy of alpha particle is around 4000 MeV, whereas its kinetic energy is few MeV. So we don't need to use relativistic formula, but we can use non-relativistic one, that is p square over 2 twice m alpha. Okay. So let's move on to third question. Atomic mass of radon and AT are given to be 204. Atomic mass unit. What is the Q factor of beta plus process? So here for beta plus, if we start with the nucleus X with atomic mass A and atomic number Z, under beta decay it becomes, let's say, Y, and so here proton becomes a neutron. So that's why atomic number decreases by 1 plus positron plus neutrino. Okay. So this is the beta plus decay. We have to determine Q factor of this process. So Q factor of beta plus will be mass of X, nuclear mass of X, minus nuclear mass of Y, minus mass of positron, okay, and so we want to convert it to atomic mass. Since atomic masses are provided in the question, so atomic mass, so nuclear mass will be equal to atomic mass of X minus mass of Z number of electrons, just like before, and mass of positron and mass of electron are the same, minus atomic mass of Y minus, since there are Z minus 1 number of protons, now there will be Z minus 1 number of electrons as well, so minus mass of positron. Let me write it as mass of electron, or you should remember that mass of positron is same as mass of electron. So mx minus z m electron minus my plus z m electron minus m electron minus, so Q factor of beta plus decay becomes mass of X minus mass of Y minus 2 times mass of electron. Okay. And here for us X is radon and Y is this AT. So these two masses we will be using, and we have to find out the answer in the unit of MeV. So it's better to convert all these atomic mass units to MeV and then substitute. So the beta decay process here is Rn 86 is becoming (85) plus positron plus neutrino. Okay. decay is equal to mass of X this is mass of X, this is mass of Y, minus, so these are in atomic mass units, so I'll convert it to MeV. So one atomic mass unit is 931.5 MeV minus 2 times mass of electron, which is 0.511 MeV. Okay, so and this comes out to be 4.24 MeV. Okay, so B is the correct option here. Okay, let us move on to fourth question. Consider the beta decay. Is this an allowed or forbidden decay? Is it Fermi type or Gamma-Taylor type? So, okay. So the decay process is beta minus decay. Calcium 20, 46 plus electron plus antineutrino, and IP of the parent nucleus is 2 minus, of the daughter it is 0 plus. Okay, okay, so let us first look at the parity conservation. Okay, so parity of potassium should be equal to parity of calcium times parity of electron times parity of antineutrino, and we know parity of electron and parity of antineutrino both are 1. So, and okay, sorry, there is minus 1 to the power L, where L is the orbital angular momentum. And we can see parity of calcium is plus and parity of potassium is minus. So right, so minus 1 to the power L is equal to minus 1, so which means L has to be odd. And we know that L greater than 0, if L greater than 0, then that beta decay is less likely to occur. But since L has to be odd here, L cannot be 0. So let us start with L equal to 1. Let L equal to 1. So the thing is, whether it is allowed or forbidden is already clear to us, because since L has to be odd, L cannot be 0. So that means the decay is forbidden. Now we want to answer whether the decay is Fermi type or Gamma-Taylor type. So any one among these two options will be correct, but we also need to understand whether it is Fermi type or Gamma-Taylor type. And since L greater than 0 decays are less likely to occur, we will start with L equal to 1 and see whether it is Fermi type or Gamma-Taylor type. Okay. So in order to see that, we now need to do angular momentum conservation. Okay, so angular momentum of parent nucleus calcium plus spin of electron antineutrino plus the orbital angular momentum. So we know that electron and antineutrino both are spin half particles. So let's denote by S. Direct sum of S electron plus antineutrino, which is half plus half, is equal to 1 or 0. I mean, it can take value 1 or 0. And if S is equal to 0, then the beta decay is Fermi type. And if S equal to 1, then Gamow-Taylor type. Okay. Okay. So let us then compute this right hand side. For say if S is equal to 0, then what happens? Let us see. It will give you, so angular momentum of calcium is 0, so this is 0 plus L is 1, since we have considered L to be 1 here, so it will give you just 1. But on the left hand side we have angular momentum of potassium, which is 2. So this is S is equal to 0 is not possible, not equal to angular momentum of potassium. So S is equal to 0 is discarded. If S is equal to 1, let us see then whether the angular momentum conservation holds or not. Calcium plus right hand side will give us, so I calcium is 0, this is 1 plus 1, so this can give you 2. So we are getting value 2, right, from the right hand side, and angular momentum of potassium is 2, so S is equal to 1 is possible. So that means the beta decay process is forbidden decay, because L is not 0 but greater than 0, so it is forbidden decay, but it is Gamow-Taylor type, because S is equal to 1 has to be the case. So the correct option then becomes D. Is this clear, or you have any doubts? Then I will explain it again. So let me reiterate the process. First you need to do parity conservation and see whether L has to be odd or even. If it is even, then you can start with L equal to 0 and see the angular momentum conservation, for which is, whether angular momentum conservation holds true for S equal to 0 or S equal to 1. And if when you do parity conservation and you see L has to be odd, you will start with L equal to 1 and then see the angular momentum conservation. And when you do angular momentum conservation, you have to see for which value of S this equation holds. Since here S equal to 0, if we consider, right hand side comes out to be only 1, but the angular momentum of potassium is 2, so S equal to 0 has to be discarded. And if we consider S to be 1, then we can see that the right hand side gives value 2 as well. So value 2, these values are also there, but value 2 is there, so that is what we are concerned about. So that means here beta decay is forbidden and gamma Taylor type. Okay. Atomic masses of xenon, Cs and Ba are given. Which of the following statements are correct? The single beta minus decay of xenon is not energetically favored. The single beta minus decay of xenon is energetically favored but is highly forbidden. So let us check the first statement whether it is correct or not. So beta minus decay, xenon will become since beta minus decay converts one neutron to proton, so that's why proton number gets increased by 1, then electron comes out and antineutrino comes out. So beta minus decay, we have to see whether this process is energetically favored or not. So how do we check that? We need to see whether the Q value of this decay process is greater than 0 or it is less than 0. If it is greater than 0, it's energetically favored. Yeah, that's right. So if Q is greater than 0, that means it is energetically favored. If Q is less than 0, then that means it is not energetically favored. And as we already saw that for beta minus decay, Q value is mass of the parent nucleus. So basically these are atomic masses, since I am not writing anything on the superscript, minus mass of the daughter nucleus. Okay, and if we compute that, so mass of xenon is 135.90722. Just by looking at these values also you can see whether it is greater than 0 or less than 0. So this is greater, less than 0, so that means it is not energetically favored. So option A is correct. Okay. Option B says the single beta minus decay of xenon is energetically favored but is highly forbidden. So as we already figured out that it is not energetically favored, so that means this is incorrect. We don't even need to check the second statement, because the first statement itself says it is energetically favored, but that is not so, since Q value of this reaction is less than 0. So B option is incorrect. Let us see C option. It says double beta decay of xenon is an allowed reaction and is energetically favored. So what does double beta decay mean? You have xenon, and under double beta decay it will become, and 136 electrons will come out, so antineutrino will come out. So this is the double beta decay, or it can also be written as beta beta decay. And we need to see whether it is energetically favored or not. So let us see. Q of this decay process, beta beta decay, will be mass of xenon minus mass of Ba, and 135.90722 minus 135.90458. Since this value is small compared to that, so this is of course greater than 0. So that means the double beta decay of xenon is energetically favored. We also need to see whether it is an allowed reaction or not. So in order to see that, what do we need to check? We need to check whether L equal to 0 is possible or not. If L equal to 0 is not possible, then it is forbidden, it is not an allowed decay. So, and how do we check whether L is equal to 0 possible or not? We need to see parity conservation. So let us see that. Of xenon is 0 plus, and it is also 0 plus. So we can see that there is no parity change. Parity of xenon since this is also plus 1, this is also plus 1, and these are also plus 1 as we said in the earlier problem. So that means minus 1 to the power L equal to 1. That means L is even. So therefore L is equal to 0 possible. So it is allowed reaction. Double beta decay of xenon is an allowed reaction, and it is energetically favored. We are saying from the question itself. In the question it is given that xenon is having angular momentum 0 and parity plus 1. So the values given inside this bracket are nothing but I, P. So I means the angular momentum and P means its parity. Okay. Okay. So yeah. So then the C option is correct. It is allowed reaction, Fermi type. Okay, sorry, Fermi type we haven't checked, but it is allowed reaction. And D option says double beta decay of xenon is energetically favored but is forbidden. So this is not correct because L is equal to 0. Okay. Consider the 4 isotopes with these masses. Their nuclear spins and parities are given. Which of the following sentences are correct? Okay, so let us check one by one. Option A, it says carbon 13 is stable against beta minus and beta plus decays. So by stable it means that particular decay is not possible. So in order to see whether a particular beta decay process is possible or not, we need to check whether its Q value is greater than 0 or not. If it is greater than 0, then the decay process is possible, and then we will say that the carbon 13 is not stable. But if it is less than 0, then that means that decay process is not possible, and hence carbon 13 is stable against both beta minus and beta plus decays. So Let us check. 13 under beta minus, neutron gets converted to proton, so proton number gets increased by 1, so it becomes quad. Plus electron plus antineutrino. Okay, so Q value of this reaction Q beta minus of 13C6 becomes mass of C minus mass of nitrogen. It is equal to, so all the masses are given again, atomic masses, okay, in this entire tutorial. So 13.00335 is the mass of carbon minus 13.00574. Obviously it's less than 0, so that means this decay process is not possible. So carbon 13 is stable against beta minus. Let us check whether it is stable under beta plus as well. So the beta plus decay of carbon will be boron 13.5 plus positron plus neutrino. So beta plus Q value of beta plus decay is equal to mass of carbon minus mass of boron, which is minus 13.01778. So again it is greater than this value, so this is less than 0. So that means option A is correct. Carbon 13 is stable against both beta minus as well as beta plus. Okay, let us check option B now. It says beta minus decay of nitrogen is not favored energetically, however its beta plus decay is energetically allowed. So we again have to check the similar thing, Q value for nitrogen now. Okay, so let's do that. Nitrogen 13.7 becomes 8, 13 plus under beta decay. So Q value will be mass of nitrogen minus mass of oxygen. Again the same, minus mass of oxygen is 13.02482. Yeah, 02482. So this is again less than 0. So beta minus decay of nitrogen 13 is not energetically favored. So the first statement is correct. Let us check the second one. Its beta plus decay is energetically allowed or not. So under beta plus decay, it will become carbon 6 plus. Okay, so Q value mass of nitrogen minus mass of carbon 13.00574 minus mass of carbon was 13.00335. So this is greater than 0, right? So that means the second statement is also correct. Its beta plus decay is energetically allowed. So A and B both are correct. Let us check C option. It says beta minus decay of boron 13 is most probably a gamma Taylor type decay. Beta minus of Is it beta minus? Yeah, beta minus. Okay. 13, 5 under beta minus will become carbon plus electron plus antineutrino. It says, okay, we have to check whether it is gamma-Taylor type or not. Okay, so for that we first need to figure out the L value, angular momentum, that we will do using the parity conservation. So we need to use these parities and spins, angular momentum, yeah. So 3/2 minus for boron, and it is half minus for carbon. Okay, so there is no parity change, and therefore minus 1 to the power L will be, okay, let me do it properly. So minus 1 for boron. Okay, I am doing parity conservation here. So for boron it is minus 1, for carbon it is again minus 1, for electron it is plus 1, for antineutrino it is plus 1, and then minus 1 to the power L comes. So minus 1 to the power L is equal to plus 1. So that means L has to be even. Okay, so therefore we consider L to be 0. Okay, and now we need to do angular momentum conservation to see whether it is gamma-Taylor type or not. Angular momentum of boron is equal to carbon plus the S value, that is S electron. Okay, let me write it down, plus L, and this we will say is L plus L. So if S equal to 0, then RHS of angular momentum conservation equation will give us, will be equal to, this is half given to us, so half plus 0, L is also 0, so this is half. So therefore, but I boron is 3/2, so S equal to 0, not possible. So it is indeed not Fermi type, so it has to be then gamma-Taylor type, but let us check it. Will give us half plus 1 plus 0, so 3/2 or half, so 3/2 is there, therefore S equal to 0 is a possibility. So S equal to 1 is possible. Therefore C option is also correct. Beta minus decay of boron 13 is most probably a gamma-Taylor type decay. Alright, let us now see the option D. Beta plus decay of oxygen 13 is energetically allowed. So let's check the first statement. C. Beta, what was it? Beta plus decay of oxygen 13. Okay, so that will become nitrogen. Plus positron plus neutrino. First statement was it is energetically allowed. So we need to look at the Q value of this reaction. Q value of beta plus decay of oxygen, mass of oxygen minus mass of nitrogen. So mass of oxygen was 13.02482 minus 13.00574 atomic mass unit. Okay, so it is greater than 0. That means the beta plus decay of oxygen is energetically allowed So now we need to check the second statement, but it is forbidden decay considering the angular momentum conservation. So we need to check what is the S value. Okay, so for that we first see the parity conservation. Oxygen it was 3/2 minus, I guess. Yes, 3/2 minus, and then that is half minus. And half minus, so no change in parity. So no change in parity. That means minus 1 to the power L has to be plus 1, which says L is equal to even. Okay, so let's consider L to be 0. And see the angular momentum conservation. Oxygen is equal to nitrogen plus S plus L. Okay. If S equal to 0, then we have just half, right? But oxygen is 3/2, so S equal to 0 not possible. So of course then S equal to 1 will be the case. 3/2, half. Okay, which is angular momentum of oxygen. So that means it is a forbidden decay considering angular momentum conservation. Oh, I didn't have to check whether it is S equal to 0 or 1. I'm sorry. But I just had to check whether L equal to 0 is a possibility or not. So it says it is a forbidden decay, but we saw that L equal to 0 is possible because there is no change in parity. So minus 1 to the power L was plus 1, and that means L can be even, so L equal to 0 is a possibility. That means the decay is allowed and not forbidden. So D option is incorrect. I didn't have to check whether it is S equal to 0 or not, because it is not asking whether it is Gamow-Taylor type or Fermi type. Okay. Anyway, so it is basically it is allowed and Gamow-Taylor type. Okay. Let's solve the 7th question. A nucleus in the spin parity state of 7/2 minus undergoes a gamma radiation to its ground state with spin parity 5/2 plus. This gamma radiation process may be categorized as which one? So a nucleus X excited in the excited state. So this is the gamma decay. Of the excited state nucleus is 7/2 minus, and in the ground state it is 5/2 plus. Okay. Okay. So here there is change in parity. So let us do again parity conservation. if it is electric transition, then we know that the change in parity, which was denoted as delta pi in the lecture, this is minus 1 to the power L. If it is magnetic transition, then delta of pi is equal to minus 1 to the power L plus 1. Okay, so I initial is equal to I final into minus 1 to the power L here, and here I initial is equal to I final into minus 1 to the power L plus 1. Okay, so I initial is minus 1, sorry, I mean parity. Okay, we are doing parity here. Minus 1 is equal to plus 1 times minus 1 to the power L. So minus 1 to the power L is equal to minus 1. And here again minus 1 is equal to plus 1 times minus 1 to the power L plus 1. So basically there is change in parity, so that means minus 1 to the power L plus 1 is minus 1. So that means for the electric transitions, L has to be odd, and for the magnetic transition, L has to be even. So among these options, we can either have E1 or we can have M2. So this quantity is nothing but L, the order of the transition. Okay, so for electric transition, L has to be odd, so E1 is possibility, and for magnetic transition, L has to be even, so M2 is a possibility. Now we also need to see which one among these two will be the correct option. So we know that for same order, the magnetic transition is less likely to occur. So these properties were explained in the lecture. So let me just write it down. And we also know that higher order transitions are less likely to occur. Higher order meaning value of L, higher L value. Okay, higher order transitions and also for same order, for same order, the magnetic transition is less probable compared to electric transition. But we can already see that the correct option will be E1 and not M2, because magnetic transitions are less likely to occur, and also higher order transitions are less probable. Okay. Okay, so this 8th question. So which of the following, so this is the last question, which of the following is correct regarding internal conversion? It is a reaction in which an excited state of nucleus de-excites, emitting a photon. So as you know, this is nothing but gamma decay. And not an internal conversion. What about option B? It says electron in the beta decay remains in the atom as an atomic electron, is known as internal conversion, but you know in beta plus decay or beta minus decay, and if it is beta minus, one electron comes out, and if it is beta plus, one positron comes out. So this is also not correct. What about option C? It says when an excited nucleus de-excites with ejecting one of the atomic electrons, it is called internal conversion. Well, it's correct. And D option is saying when an atomic electron is absorbed by the nucleus, converting a proton to a neutron, it is called internal conversion. We know that it is electron capture. One positron comes out. Okay, so the internal conversion is this option C, when an excited nucleus de-excites, ejecting one of the atomic electrons. That process is called internal conversion. Okay, we are done with this assignment 4. Let me know if you have any doubts, or we can stop here. Last step of how we say parity of xenon. Okay, that question was answered. Last step, can you tell me for which particular question I should explain the last step? Are you there still? Third question. Okay. Last step of third question. Well, so here it is just Q factor of beta plus decay. I'm sure you are asking some other question. Would you please unmute yourself and then tell me which particular question? Well, if it is third question, then it is just the Q value of beta plus decay, and just we need to use this expression of Q value for beta plus decay and then get the answer in MeV units. Since the question is asking in MeV units, we have converted atomic mass unit to MeV just by multiplying with 931.5 MeV. Is that what you are asking? Okay, is this clear then? Okay then, yeah. Okay then, let us stop here. We will meet in the next week.